Okay, let's unpack this.
Welcome back to the deep dive. Today we're plunging into the fascinating, practical world of machine learning classification models. We've got an incredible stack of sources from IIT Madras's machine learning practice course, really filled with demonstrations on how these algorithms are actually built, trained, and, well, evaluated. Our mission today is to cut through the jargon, give you a clear, engaging understanding of these powerful tools. We'll use real-world examples like recognizing handwritten digits or categorizing text.
And what's truly compelling here, I think, is not just what these models can accomplish, but the intricate how behind their operations. And the critical decisions involved in making them effective. We'll explore the nuances of various classifiers, from the foundational logistic regression right up to the speedy naive Bayes. And crucially, we'll look at how we rigorously measure their success beyond just, a simple accuracy score. All right. So what does this all mean for you, the listener? Whether you're a data science enthusiast looking to deepen your practical understanding, maybe prepping for a big meeting where these terms will undoubtedly come up, or just intensely curious about how AI makes sense of the world, this deep dive is your shortcut, your way to being genuinely well-informed. We're packed with surprising facts and practical insights you can grasp quickly and confidently.
Yeah, let's dive in.
Okay, let's kick things off with a true legend in the machine learning world. Logistic regression. Our sources aptly describe it as the workhorse classifier. It really dominated before the deep learning era, didn't it?
Oh, absolutely. It's incredibly versatile. It can handle binary problems like a simple yes-no decision, but it also scales up to multi-class, identifying one of several categories, and even multi-label challenges, where an item can belong to multiple categories at once.
Think of it as the sturdy, reliable hammer in a carpenter's toolkit, indispensable for countless tasks because it's so adaptable.
Exactly. Before the rise of deep neural networks, it was often the default, the go-to choice for solving real-life classification problems. Even those involving, hundreds of thousands of features. It was surprisingly robust.
Okay, so where are we going to see this workhorse in action today?
Our primary playground for today's demonstrations, and where we'll see logistic regression really shine, is the widely known MNIST dataset.
Ah, MNIST, the handwritten digits.
That's the one. It's a treasure trove of 70,000 images, each a meticulously handwritten digit ranging from 0 to 9. Now, while each image is quite small, just 28 by 28 pixels,
Which sounds tiny.
it does, but that seemingly modest size translates into a significant amount of data for a model to process. Precisely 784 individual features, one for each pixel's intensity value. That's a rich, granular input space for any classifier to navigate.
Okay, 784 features. That's quite a bit to chew on.
It is. And to simplify things for learning, especially when we're first grappling with these core concepts, we often convert this naturally 10-class problem into a simpler binary classification task.
How does that work?
For instance, we might create what's called the zero detector. In this focus scenario, images of the digit 0 decaro are explicitly labeled as 1, signifying a positive match, and all other digits from 1 to 9 are labeled as 0, indicating they are not a 0.
So it becomes a simple, is it a 0 or is it not a 0 question?
Exactly, a binary choice. It's also worth noting that for some specific classifiers, like the rich classifier we'll discuss later, these negative labels might actually be -1 instead of 0.
Why is that?
It reflects the specific mathematical formulation of that algorithm and its underlying objective function. Different models sometimes like their labels formatted differently.
Got it. Now, before any machine learning model, logistic regression or otherwise, even gets a glimpse of this raw pixel data,
Right.
there's an absolutely crucial first step, often overlooked by beginners: data pre-processing. Why is this so vital, especially for our MNIST images?
Absolutely vital. For the MNIST images, pixel intensities range from a dark 0 to a bright 255. Imagine trying to feed numbers that vary so wildly into an algorithm that's trying to find subtle patterns.
Yeah, that sounds messy.
It can be like trying to navigate a landscape where one step moves you an inch and the next moves you a mile. It's just uneven. So to solve this, these pixel intensities are scaled, or normalized, to a much more manageable 0-1 range using a technique called min-max scalar.
Okay, scaling to 0, 1.
And this scaling is not just a nice to have, it's absolutely vital, especially for models that use gradient descent as their optimization procedure.
Why specifically for gradient descent?
Well, without it, features with vastly different ranges, say pixel intensities from 0 to 255, versus maybe a binary feature we added, like is it bold, 0 or 1, would create very different slopes or gradients in the loss landscape. Imagine trying to descend a mountain where one direction is a gentle slope and another is a sheer cliff.
Your steps would be all over the place.
Exactly. Your optimization steps would be uneven, potentially oscillating wildly, struggling to find the bottom efficiently. Scaling ensures all features contribute proportionally, smoothing out this landscape for more stable and faster convergence.
Makes sense. Any pitfalls to avoid during scaling for images?
Yes, and here's a key caution when dealing with image data. Avoid mean centering.
Mean centering. What's that?
It's subtracting the mean value from each feature, centering it around 0. While it's common and often helpful in other contexts for numerical data, for images, it can inadvertently remove the true 0 values.
Because 0 pixel intensity means black or no ink.
Precisely. And that 0 is meaningful here. It represents the absence of ink or a background pixel. You definitely don't want to inadvertently remove meaningful information from your data before the model even starts to learn.
Good tip. Okay, so we've got our data meticulously prepared, scaled nicely between 0 and 1. But now for the core question. How does a logistic regression model actually learn from all these perfectly scaled pixels? What's its fundamental mechanism, and what's it trying to achieve through all that number crunching?
That's the million-dollar question. At its heart, the logistic regression model first computes a linear combination of the input features.
Linear combination, like in basic algebra.
Exactly like that. Think of it as taking each pixel's scaled intensity, multiplying it by a specific numerical weight, which the model has to learn, and then adding all these weighted pixel values together. Plus, there's usually an intercept term, like the b in ymx plus p.
Okay, so weights times pixels, summed up.
Right. This creates a single numerical score, a sort of raw propensity score. But a score isn't a probability, and for classification, we ideally want probabilities.
How does it get from score to probability?
So this raw score is then passed through a very clever sigmoid nonlinear function.
The sigmoid form? I've heard of that. It's S-shaped, right?
That's the one. This function takes any real number, positive or negative, large or small, and smoothly transforms it, or squashes it, into a value strictly between 0 and 1. Think of it as a probability translator. If that linear score is very high, say positive infinity, the sigmoid output gets very close to 1. If the score is very low, negative infinity, the output approaches 0. And if the score is exactly 0...
0.5, right in the middle.
Exactly, 0.5. This squashing property is what allows it to output a meaningful probability that the input belongs to the positive class. In our case, that the digit is out of the row.
Okay, so it generates these probabilities, but how does it know if it's doing well? And how does it adjust itself to get better? What's the learning goal?
Good question. The model's real goal, the learning objective, is to figure out the best set of these internal parameters, essentially, the optimal weights for each pixel and that intercept term. This is achieved by optimizing, or really minimizing, what's called a cross-entropy loss function. It's also widely known as log loss.
Cross-entropy or log loss, what does that measure?
It measures how far off the model's predicted probabilities are from the true labels, the actual years and ones in our training data. Intuitively, if the model predicts a high probability for a class that turns out to be wrong, the cross-entropy loss will be very high, penalizing it heavily. Conversely, if its predictions are confident and correct, the loss will be low. The lower the loss, the better the model's parameters align with the data.
And how does it minimize this loss?
This minimization process is typically carried out using an optimization procedure called gradient descent.
Gradient descent? Sounds like going downhill.
That's a perfect analogy. Imagine you're blindfolded on a mountainous terrain, trying to find the lowest point, the valley floor. You can feel the slope around your feet, right?
Yeah.
Gradient descent is like taking small steps in the direction of the steepest downhill slope. It iteratively calculates how the loss changes with respect to each weight that's the gradient, and adjusts the weight slightly in the direction that reduces the loss the most. Slowly but surely, step by step, it finds the set of weights that minimizes the overall loss.
Okay, that makes sense. Now, before we even put a sophisticated model like logistic regression through its paces, you mentioned establishing a baseline. This gives us something concrete to compare against, right? A measure of our model's real intelligence.
Exactly. It's always smart to know what dumb looks like first. Our sources demonstrate this beautifully by using a dummy classifier. This is set to simply always predict the most frequent class in the training data.
Okay, so for our zero detector, most digits aren't zeros, right?
Precisely. In the MDS dataset, only about 10% of the images are zeros. The other 90% are digits 1 through 9. So this dummy classifier, simply by always predicting not 0, class 0 in our binary setup,
Gets it right 90% of the time.
exactly. It achieves a staggering 90% accuracy just by guessing the majority class every single time.
Wow. That's deceptively high.
It really is, and it highlights a crucial, non-obvious point. Accuracy alone can be a highly misleading metric, especially when you're dealing with imbalanced data sets like this one. It means our sophisticated logistic regression model needs to do significantly better than 90% accuracy by actually learning to distinguish zeros from non-zeros to be truly useful.
If your model only gets 91% accuracy, it's barely doing better than the dummy guesser for the actual zeros.
That's right. It's a powerful diagnostic insight. It tells you the real challenge lies in correctly identifying that minority class.
That's a great cautionary tale. Now, what's particularly fascinating is how we can implement logistic regression using SGD classifier in Sklern. That seems counterintuitive at first glance. How does a stochastic gradient descent classifier morph into a logistic regression model?
Yeah, the naming can be a bit confusing. The SGD classifier is actually a general-purpose linear classifier. It's incredibly flexible because it can handle various loss functions, and the loss function dictates its objective, what it's trying to minimize.
So you just tell it which loss function to use.
Exactly. If you explicitly set its loss parameter to log, it magically transforms itself. By telling it to optimize for log loss, which, remember, is the same as cross-entropy loss, it starts behaving exactly as a logistic regression classifier. It uses that sigmoid activation internally and minimizes the cross-entropy loss we just discussed. Minimizing log loss is the mathematical objective of logistic regression.
So SGD classifier with loss log is logistic regression.
Pretty much, yes. By default, it also comes with some built-in L2 regularization. We'll talk more about that, indicated by penalty of 2, with a default rate alpha 0.00001.
And the stochastic part of SGD classifier, what does that mean compared to regular gradient descent?
Good question. Unlike standard batch gradient descent, which calculates the gradients based on the entire training dataset before making a single update to the weights, stochastic gradient descent, SGD, calculates the gradient and updates the weights based on just a single randomly chosen sample or a small mini batch of samples at a time.
Okay, so it takes lots of small steps based on tiny bits of data.
Right. This introduces more noise or randomness into the updates, making the optimization path a bit more zigzaggy compared to the smoother path of batch gradient descent.
Does that cause problems?
It can make convergence a bit jumpier, but it also has advantages. It makes training dramatically faster and more scalable for very large data sets because you don't need to load everything into memory at once. And sometimes that very noisiness can actually help the model escape shallow local minima in complex loss landscapes. Think of it like shaking a marble out of a small divot on its way down a hill, helping it find the true global minimum.
Interesting. So how can we watch this SGD learning process happen?
To really observe how this learning unfolds over time, our sources show a brilliant technique. Using the partial fit method. You use partial fit with warm start, true, and train iteratively, maybe feeding it mini batches one by one. This allows us to plot a learning curve.
The learning curve
Showing the log loss after each iteration or each batch. In an ideal learning curve, which is exactly what our sources demonstrate, you'll see the log loss steadily decrease with each passing iteration or FOC.
Like a nice smooth downhill slope on the graph.
Precisely. This consistent downward trend is a clear and powerful sign that the model is indeed learning effectively, continuously refining its parameters to better fit the training data and reduce the errors in its predictions.
And what if the curve doesn't look like that?
If you saw the loss plateau very early, or even worse, start to increase, that would signal a problem. Maybe your learning rate is too high, causing it to overshoot the minimum, or maybe the model isn't complex enough, insufficient capacity. Or perhaps it simply learned all it can from the data. It's a great diagnostic tool.
Okay, diving deeper into how these models prevent common pitfalls, let's talk about the crucial role of regularization. Many people hear this term, know it's important, but what exactly is it doing under the hood, and how does it prevent something called overfitting?
Right. Its main purpose is precisely to prevent overfitting. Overfitting happens when a model learns the training data too well. It starts picking up on noise and specific quirks of that particular data set rather than the underlying general patterns you actually wanted to learn.
Like memorizing the answers instead of understanding the concepts.
Exactly like that. Imagine a student who memorizes every single answer to every practice question, but doesn't actually understand the concepts. They'll ace the practice test, but fail the real exam with new, unseen questions. That's overfitting.
So how does regularization stop that?
Regularization, like L2 regularization, which is controlled by the alpha parameter in SGD classifier or the C parameter in logistic regression, confusingly, C is often more in alpha, addresses this by adding a penalty term to the loss function. This penalty discourages the model from becoming overly complex or assigning excessively large weights to any particular feature.
It penalizes big weights.
Yes, it's like telling the model, hey, try to fit the data well, but don't get too confident or too specific with any single feature. Keep your weights modest and spread out the importance. This forces the model to find simpler, more generalizable patterns that are more likely to perform well on new, unseen data. It prefers simpler explanations over complex ones that fit the training noise perfectly.
Our sources beautifully demonstrate this by actually training logistic regression without regularization. How do you turn it off?
For the standard logistic regression estimator in Sklearn, you do this by setting the C parameter to a very large number, effectively infinity. Since C controls the inverse of the regularization strength, infinite C means zero regularization penalty. For the SGD classifier, you'd set the regularization strength parameter, alpha, directly to 0.
Okay. And what happened in the zero detector example when they did that? Was there a huge difference?
This is where it got really interesting and quite unexpected based on the theory. For the zero detector example, even the non-regularized SGD classifier with alpha 0 still showed 67 features pixels, in this case with weights that were exactly 0.
Wait, zero weights even without the penalty of pushing them towards zero?
Exactly. And this was very much like its regularized counterpart, which also had a similar number of zero-weighted features. It seems counterintuitive, doesn't it?
It does. What does that tell us? Does it mean regularization wasn't needed here?
It suggests something profound. Sometimes the inherent structure or sparsity of your data can act as its own silent regulator. It challenges the conventional wisdom that explicit regularization is always strictly necessary. It suggests that in some cases, especially with sparse data like MNIST, where many pixels are just background, the model might naturally gravitate towards simpler solutions, effectively performing a form of feature selection on its own by assigning zero weight to uninformative pixels.
So the data itself is kind of pushing the model to ignore useless stuff.
It's almost as if the data itself is saying, these pixels aren't contributing much, let's ignore them. This means if your model performs well, even without explicit regularization, it might be a powerful diagnostic insight. It could signal that you're working with naturally clean or sparse data, which is a great place to be.
How did the performance compare, though? Was the non-regularized one worse?
While the non-regularized model did exhibit a slightly higher loss value, its overall performance in terms of metrics like accuracy, precision, and recall was remarkably close to the regularized one for this specific task. This hints that for this particular problem, the benefits of L2 regularization might have been subtle. Perhaps the data itself is so well behaved that it doesn't suffer severely from overfitting even without the explicit penalty.
But we shouldn't generalize this, right? Regularization is still usually important.
Oh, absolutely crucial not to overgeneralize. For noisier or more complex datasets, or datasets with highly correlated features, regularization remains absolutely vital to prevent overfitting and ensure the model generalizes well. This MNIST example is just an interesting edge case.
Okay, so we have these internal parameters, the weights, learned by the model during training. But then there are other settings we have to choose before training even starts. Expert, here's where it gets really interesting. Hyperparameter tuning. What's the difference between these learned parameters and hyperparameters, and why is tuning the latter so critical?
You've hit on a core distinction, and it's fundamental to practical machine learning. When you're building models, you quickly realize there are two kinds of parameters. First, there are the model's internal parameters, like those weights and the intercept we just discussed. These are learned directly from the data during the training process, using methods like gradient descent to minimize the loss function.
The model figures those out itself.
Right. Then there are hyperparameters. These are higher-level settings that you, the data scientist, set before training begins. They control the learning process itself. Examples include the regularization rate, that C for logistic regression, or alpha for SGD classifier, or even the learning rate, ATOD0 for SGD, that controls the step size in gradient descent.
So they're like knobs on the training machine.
That's a great way to think about it. And these hyperparameters are not learned by the model itself during training. Finding the best values, the best settings for these knobs, can significantly impact your model's ultimate performance on new, unseen data.
So it's not enough to just pick a model, you have to tune it.
Precisely. It's truly a critical step in the machine learning workflow, moving you from a generic, off-the-shelf model to one that's optimally suited for your specific data and problem.
How do we find these best values? Guessing seems inefficient.
Definitely not guessing. One of the most common and systematic methods is grid search CV.
Grid search. Sounds methodical.
It is. You define a discrete set or grid, of possible values for each hyperparameter you want to tune. For example, you might say, for the regularization parameter C, I want to try values of 0.001, 0.01, 0.1, 110, and 100. Grid Search CV that exhaustively trains and evaluates the model using cross-validation for every single combination of these values in your grid.
Like trying every single size and width combination for a pair of shoes.
Exactly. It guarantees you'll find the best combination within your defined grid, according to whatever performance metric you choose. Our sources show an example where it might find that C0.1 yields the best F1 score, perhaps around 0.9579, for logistic regression classifier, proving that specific choices lead to measurable improvements.
What's the downside? Sounds computationally expensive.
It can be very computationally expensive, yes.
Yeah.
Especially if you have many hyperparameters to tune, or if the range of values you want to try for each is large, the number of combinations explodes quickly.
So what if you don't have the time or computing power for grid search?
That's where randomized search CV comes in. It offers a more efficient and often equally effective alternative, especially when your search space is massive or your budget is limited.
Randomized search, how does that work?
Instead of trying every single combination like grid search, randomized search CV samples a fixed number of parameter settings randomly from specified distributions. For instance, for a learning rate, instead of defining a fixed grid, you might specify a log uniform distribution between, say, 0.00001 and 1. Randomized search CV will then randomly pick values from that distribution for a predefined number of iterations. For example, 50 trials.
So it explores the space without trying everything.
Exactly. It allows you to explore a much larger potential space more quickly, even if you don't exhaustively check every single point. It's like knowing the best shoes are probably in aisle 7, but instead of trying every single pair, you randomly sample a good number of pairs from that aisle until you find a great fit. It prioritizes exploration over exhaustion, often finding near-optimal results much, much faster than grid search.
That sounds very practical. Are there other tuning methods?
Yes, and for logistic regression specifically, Slurm even offers a specialized estimator called Logistic Regression CV. This convenient tool automatically performs cross-validation internally to find the optimal C values across a predefined range. It essentially bakes the hyperparameter tuning process, specifically for the regularization strength C, directly into the estimator itself.
Oh, that's handy. Less setup required.
Exactly. It can save you a lot of manual setup code and makes the process incredibly streamlined if you're primarily focused on tuning the regularization for logistic regression.
Now, you mentioned these tuning methods optimize for a specific performance metric. Can you elaborate on that?
Yes, this is critical. The best hyperparameter value that grid search CV, randomized search CV, or logistic regression CV finds is always optimized for a specific scoring function that you provide. While the F1 score is often used as a default or a good starting point because it elegantly balances precision and recall.
Precision and recall. We'll get more into those soon, right?
We will. But the point is, you also have choices. You could tell the tuning process to maximize precision specifically or maximize recall specifically. The choice depends entirely on what aspect of performance is most important for your particular problem and its real-world consequences.
Right. This raises an important question. When you're faced with these choices, optimized for F1, precision, or recall, how do you decide which scoring function aligns best with the actual impact of your model? What are the trade-offs?
That's the crux of it, really. Understanding those trade-offs is key to building models that are not just statistically good, but practically useful.
Okay, let's dive into that. As we saw with the 90% baseline accuracy for our zero detector, relying solely on accuracy can be really deceptive, especially with imbalanced classes. That baseline was achieved just by predicting not zero every time, because not zero is the overwhelming majority class. So what does this tell us? It means we desperately need a more nuanced view of performance than just that single, potentially misleading accuracy number.
Absolutely. This is where we introduce the triad of key metrics that provide that necessary nuance: precision, recall, and the F1 score. Let's break them down.
Okay, first up, precision.
Precision answers the question. Of all the instances the model predicted as positive, for example, predicted to see how many were actually positive, actually zeros, it's all about avoiding false positives. You want to be sure that when the model says something is positive, it's correct.
Give me an example.
Think of a spam filter. High precision means that when an email is flagged as spam, it's very likely to be spam. You minimize the risk of important emails, non-spam, being incorrectly sent to the spam folder, a false positive.
Got it. Avoid putting good emails in the spam folder. What about recall?
Recall asks a different question. Of all the instances that were actually positive, all the actual years in the dataset, how many did the model correctly identify? It's all about avoiding false negatives, finding all the relevant instances.
Back to the spam filter example.
For the spam filter, high recall means it catches most of the actual spam emails. You minimize the number of spam emails that sneak through into your main inbox. A false negative.
Okay, so precision is about the accuracy of positive predictions. Recall is about finding all the actual positives. There's a trade-off there, right?
There often is. If you make your spam filter super strict, high precision, you might miss some spam, lower recall. If you make it very sensitive to catch all spam, high recall, you might accidentally flag some good emails, low precision.
So how do we balance them?
That's where the F1 score comes in. It's the harmonic mean of precision and recall.
Harmonic mean. Why not just average them?
The harmonic mean gives lower weight to larger values and is thus more sensitive to low scores. It means the F1 score will only be high if both precision and recall are reasonably high. You can't cheat it by having extremely high precision but terrible recall, or vice versa.
Ah, okay. So it provides a single score that elegantly balances both metrics.
Exactly. It's particularly useful when you want a good balance between catching all positives, high recall, and not misclassifying negatives as positives, high precision, especially when both false positives and false negatives have significant costs.
Like in fraud detection.
Perfect example. In fraud detection, you want high recall to catch most fraudulent transactions. But you also need decent precision so you don't constantly block legitimate customer purchases, which would be a terrible user experience. F1 score helps balance that.
Okay, so looking back at our 3 logistic regression classifiers for the zero detector, the non-regularized one, the grid search CV-tuned one, and the logistic regression CV-tuned one, how did they compare on these metrics? Did tuning make a big difference here?
Our sources show that while all 3 performed remarkably similarly overall, their F1 scores were very close. The tuned models did achieve marginally higher precision or recall values, depending on which one was optimized for. For instance, Grid Search CV, when optimized for F1, happened to yield the highest precision in that run, while Logistic Regression CV maybe gave the highest recall. Both were just slightly outperforming the non-regularized model on those specific aspects.
So tuning didn't drastically change the overall picture here, but it allowed for fine-tuning specific aspects.
Precisely. It shows that tuning, even if it doesn't boost the headline F1 score by a huge amount, can still refine performance in specific important ways. Maybe need slightly higher precision, and tuning helps you eke that out. Those small gains might be crucial for a particular business objective.
Now, to truly visualize where a model gets things right, and more importantly, where it gets confused, we turn to the confusion matrix. Expert, walk us through what this powerful table actually reveals.
The confusion matrix, at its core, is a really insightful table. It breaks down a classifier's performance in exquisite detail, going beyond single summary metrics. It shows you 4 key things. True positives, TP. Correctly predicted positive instances. Said 0 was 0. True negatives, key N. Correctly predicted negative instances. Said not 0, it was not 0. False positives, FP. Incorrectly predicted positive instances, type I error. Said 0 but was not 0. False negatives, FN. Incorrectly predicted negative instances, type 2 error. Said not 0 but was 0.
So it lays out all the rights and wrongs, clearly.
Exactly. It's a diagnostic tool that gives you a complete picture of your model's classification behavior, showing not just how many errors it made, but what kind of errors they were.
What did the confusion matrix look like for our non-regularized zero detector? Where did it get confused?
It was very revealing. The confusion matrix for the non-regularized logistic regression model specifically showed that 48 examples from class 0, meaning they were actual zeros, were incorrectly predicted as class 1. The model thought they were not zeros. These are the false negatives. Conversely, 38 examples from class 1, meaning they were actual non-zeros, were incorrectly predicted as class 0. The model thought they were zeros. These are the false positives.
Okay, so 48 missed zeros and 38 non-zeros mistaken for zeros.
Exactly. Those numbers are the raw errors laid out clearly, allowing you to see precisely which type of error your model is making more often.
And what about the impact of that hyperparameter tuning we discussed? Did tuning with grid search CV or logistic regression CV shift these confusion numbers significantly?
Yes, even if marginally, tuning did refine these numbers. When we look at the impact of tuning with grid search CV, the number of these misclassified examples marginally decreased. For instance, the number of true negatives, correctly classified not 0 examples, actually increased by 2, meaning 2 fewer false positives.
A small improvement, but an improvement nonetheless.
Right. And we saw further, albeit small, improvements with logistic regression CV. Perhaps the number of true negatives went up even further, and the number of false positives went down again. This tells us that even small improvements in these specific counts within the confusion matrix, which might not massively shift the overall F1 score, can sometimes represent significant real-world impact. Reducing even a few critical errors like false positives or false negatives might be very valuable depending on the cost of those errors in your application.
So the confusion matrix gives us the counts. Are there other ways to visualize the trade-offs, especially that precision recall trade-off?
Yes, absolutely. If we connect this to the bigger picture, more advanced visualizations like precision recall PR curves and the area under the curve, AUC, provide even deeper insights, particularly useful when dealing with those imbalanced data sets.
Okay, tell me about PR curves.
PR curves plot the precision, axis against recall, x-axis, at various probability thresholds. Remember, the sigmoid function outputs a probability between 0 and 1. The classifier usually uses a default threshold, like 0.5, to decide positive or negative.
Right. Probability 0.5 means positive, 0.5 means negative.
Exactly. But what if you change that threshold? If you increase it to, say, 0.9, you'll only classify something as positive if the model is very confident. This will likely increase your precision, fewer false positives, but decrease your recall. You'll miss more actual positives.
And if you lower the threshold, say, to 0.2.
Then you'll classify more things as positive.
Yeah.
Your recall will likely go up, catch more actual positives, but your precision will probably drop, more false positives. The PR curve shows you this entire trade-off across all possible thresholds from 0 to 1. A curve that stays high and to the right represents a better classifier.
And how do the PR curves look for our three logistic regression models?
Our sources reveal that for all three classifiers, the non-regularized, the grid-cert CV-tuned, and the logistic regression CV-tuned, their PR curves overlapped significantly.
Meaning they perform similarly across all thresholds.
Exactly. It's a powerful visual confirmation that their overall performance, considering that precision recall trade-off across the board, was quite similar for this specific task. It reinforces the numerical findings from the F1 scores and confusion matrices.
Okay, and what about AUC, area under the curve?
The AUC, or area under the curve, is a single scalar value that conveniently summarizes the performance represented by a PR curve, or an ROC curve, which we'll touch on. It literally measures the area underneath the PR curve. A perfect classifier that achieves 100% precision and 100% recall across all thresholds would have an AUC of 1. A random classifier would have an AUC related to the class imbalance.
So higher AUC is better.
Yes, a higher AUC generally means better overall performance across that entire precision recall spectrum. For our three logistic regression classifiers, the AUC for their PR curves was indeed reported as roughly the same, further reinforcing the idea of their very similar overall effectiveness for this zero detector task. It summarizes that consistent performance into one number.
You mentioned ROC curves briefly.
Right. ROC curves, receiver operating characteristic curves, are another very common visualization. They plot the true positive rate, which is the same as recall, against the false positive rate at various thresholds. They are often used, especially for more balanced data sets. For these logistic regression models on the zero detector task, the sources mentioned they also showed high ROC-AUC values, indicating strong discriminative power, a good ability to distinguish between the positive and negative classes across all thresholds.
Okay, so multiple ways to look at performance beyond just accuracy. That's crucial. All right, we've successfully built and analyzed a zero detector using binary classification techniques and metrics. That's a solid foundation. But now, the natural and much more complex challenge emerges. How do these principles scale up to recognizing all 10 digits from 0 to 9 simultaneously? What does this all mean for solving a true multi-class problem?
That's exactly where we move from a simple yes-no decision to identifying one out of many possible categories. It's a common scenario in the real world. Now, how traditional binary classifiers like SGD classifier handle multiple classes is quite clever and often happens automatically behind the scenes in libraries like Slurm.
How does SGD classifier handle, say, 10 classes if it's fundamentally binary?
When you feed a multi-class problem, like the full 0-9 MNESEST to SGD classifier, without explicitly telling it to use a multi-class specific method like softmax, Slurm often automatically implements a strategy called one versus rest, OVR, sometimes also called one versus all.
One versus rest, what does that mean?
It means that instead of training one complex multi-class classifier, it creates and trains 10 separate binary classifiers under the hood. You get one classifier specifically designed to detect if an image is a 0 versus all other digits. the rest. That's our familiar 0 detector.
Hmm.
Then it trains another binary classifier to detect 1 versus all others, 0, 2 to 9, a 1 detector, and so on, all the way up to a 9 detector, 9 versus 0 to 8. So you end up with 10 independent binary classifiers.
Ah, okay. So it breaks the multi-class problem down into multiple binary problems. How does it make a final prediction then?
During inference, when a new input image comes in, it's passed through all 10 of these individual binary classifiers. Each classifier outputs a score, usually the raw score from the linear combination,
Mm.
before the sigmoid indicating its confidence that the image belongs to a specific class.
So the 0 detector gives a score, the 1 detector gives a score, etc.
Exactly. These scores don't necessarily sum to 1 or anything, they just represent how positive each individual detector feels about the input matching its target digit. The classifier that outputs the highest score then determines the final predicted digit. So if the 3 detector gives the highest score among all 10 detectors, the image is classified as a 3.
That's quite elegant. So it leverages binary classifiers to solve a multi-class problem.
It is. What's fascinating here is seeing how a complex problem, recognizing 10 different digits, is broken down into simpler, manageable binary parts. The model structure reflects this directly. The weight matrix for such a multi-class SGD classifier using OVR will have a shape of 10 rows by 784 columns plus 10 intercepts.
10 rows, one for each detector.
Precisely. Each row in this matrix represents the learned weights for one of the 10 binary classifiers, a row for the 0 detector, a row for the 1 detector, and so forth. It effectively encodes what each specific detector has learned to look for when it tries to identify its particular digit against all the others.
Okay, that's the one versus rest strategy using binary classifiers. But you mentioned there's also a more direct approach to multi-class problems, one that doesn't involve stitching together multiple binary classifiers.
That's right. This is often referred to as softmax regression, although technically it's just logistic regression configured for multinomial output. It's a more native multi-class solution.
How does that work differently?
Instead of training multiple independent binary classifiers, logistic regression in Sklearn can directly handle the multi-class problem as a single model. You achieve this by setting the multi-class parameter to multinomial and potentially choosing a suitable solver algorithm, like SAG or POBFGs, that supports this mode. This tells the model to fundamentally treat it as one multi-class problem from the outset, rather than breaking it down into separate binary OVR components.
And what happens internally when you set multi-class multinomial?
Internally, the logistic regression model uses softmax activation instead of the sigmoid function.
Softmax instead of sigmoid, what's the difference?
Sigmoid, as we saw, outputs a single probability for a binary outcome, BGA. Softmax, on the other hand, is designed for multiple classes. It takes the raw linear scores produced for all classes, 0 through 9 in our case, and converts them into a probability distribution where all the output probabilities sum up to 1.
Ah, so it gives you the probability for each digit, and they all add up to 100%.
Exactly. This is incredibly useful because it directly provides a confidence score for each possible digit. And, they represent the likelihood across all available options. So if it predicts a 0.8 probability for 3-1, it means the remaining 0.2 probability is distributed across all the other digits, 0, 1, 2, 4 to 9. This directly supports a true multi-class output, giving you a holistic view of the model's confidence.
And the model parameters, the weights, how do they look?
The model parameters, the coefficients, weights, and intercepts also directly reflect this multi-class nature. You'll have 10 sets of parameters, one for each class. 0, 9. Each set contains 784 weights, one for each pixel and a single intercept term. This means the model is simultaneously learning distinct patterns for each digit, considering all classes in concert rather than independently like in OVR.
Okay, so two main approaches, one versus rest, like SGD classifier often does by default, and true multinomial softmax regression. When we throw these multi-class classifiers at the full MNIST dataset, where do they tend to stumble? What does the confusion matrix tell us about those trickier digits?
Looking at multi-class challenges, particularly through the lens of the confusion matrix, becomes even more vital in these complex settings because you have many more potential avenues for error, 90 possible misclassification pairs. Our sources highlight common confusions observed in the MNIST dataset when using SGD classifier, likely with OVR. For instance, the digits 2 and 8 are often confused.
I can see that. A poorly drawn 2 loop could look like an 8.
Exactly. Similarly, 5 and 8 are often confused, or 5 and 3.
Yeah, 5 and 3 share that bottom curve.
Right. And 9 and 4 can also be mixed up, perhaps due to the loop and vertical stem. Interestingly, the softmax regression model, using multi-class multinomial, also showed similar patterns of confusion, such as between 3 and 5 and 8 and 5.
So the confusion is somewhat inherent to the data, not just the specific model.
It seems so. This raises an important question. What does this consistent pattern of confusion tell us? It likely reflects the inherent visual similarities between these digits, especially in varied handwriting styles. It shows how the models, much like humans, might be keying in on certain shared strokes or curves, rather than the unique identifying features, leading to these predictable mix-ups. It highlights the difficulty of the task.
How did the overall performance look in the multi-class setting? Were F1 scores still high?
When we look at the classification report for these multi-class models, the performance was generally very good. Most classes achieved impressive F1 scores well above 90%. However, some digits, like Class 8 and Class 5, the ones involved in those common confusions, consistently showed slightly lower F1 scores, often hovering around 0.87 or 0.88.
And why was that? Lower precision or lower recall?
The drop was frequently due to lower recall for those specific digits.
Meaning the models were less successful at identifying all actual instances of 8s or 5s. They missed some of them.
Exactly. They had more false negatives for those classes. They were more likely to misclassify an actual 8 as something else, like a 2, 8, or 5, or an actual 5 as something else, like a 3 or 8.
Did the different approaches, SGDOVR versus softmax, handle these tricky classes differently?
Interestingly, yes, sometimes. The sources noted that the logistic regression model, using the Pound-BFG's solver, a common choice for multinomial problems, sometimes yielded slightly better F1 scores for these trickier classes, like 8 and 5, compared to the SGD classifier using its default settings.
So the solver choice can matter.
It can. This demonstrates that even within the broad category of logistic regression, different implementations and optimization solvers can lead to subtle but potentially meaningful performance differences, especially on the harder-to-classify examples. That small boost in F1 for Class 8 might be critical depending on your application.
One of the most fascinating aspects of machine learning, especially with these pixel-based image problems, is being able to visualize what the model has actually learned. Expert, can you describe how the sources illustrate these multi-class weights? It sounds like looking inside the model's brain.
It is like peering into the model's brain, even if it's a simplified view. The sources illustrate how the weights learned for each of the 10 classes, whether from OVR or softmax, can be visualized. Since each class has 784 weights corresponding to the 28 by 28 pixels, you can reshape those weights back into a 28 by 28 grid and display it as an image.
So you get a kind of weight image for each digit.
Exactly. You get a ghostly, shadowy image or pattern for each digit from 0 to 9. These patterns essentially highlight which pixels were most important, had the highest positive weights, pixels the model wants to see for that digit, or the most negative weights, pixels the model wants not to see.
Can you give an example?
Sure. The pattern for 0 might show strong positive weights forming a ring around the outer edges of a 0-like shape, and perhaps negative weights in the center. This indicates the model has learned to look for that characteristic circular structure and the absence of ink in the middle. Conversely, for an 8 minutes, you might see positive weights concentrated where the two loops typically are. For a 1, maybe strong positive weights along a vertical line.
Wow. So it offers a powerful glimpse into what the model has learned to look for when classifying handwritten digits.
It really does. It provides a sort of visual template it uses for each number, showing which pixel patterns it associates most strongly with each class. It's a fantastic way to gain some intuition about how these seemingly black box models are making their decisions.
Okay, now, having thoroughly explored logistic regression in its binary and multi-class forms, let's broaden our horizons. Let's explore other powerful classification techniques that approach the problem from fundamentally different angles. The world of ML classifiers is rich and diverse, offering a whole toolkit for different problems.
Absolutely. It's important to know there isn't just one way to classify data. First, let's look at the ridge classifier. It offers a quite different perspective.
Ridge classifier. How does it differ from logistic regression?
Well, unlike logistic regression's probability-based approach, which uses that sigmoid or softmax activation and aims to minimize cross-entropy loss, ridge classifier frames the classification problem as a least squares classification problem.
Least squares, like in linear regression, for fitting lines.
Exactly the same mathematical principle. It's looking for the optimal weights by minimizing the sum of squared errors between its linear predictions and the actual target labels. It's essentially adapting linear regression for classification tasks. It often achieves this minimization using robust matrix decomposition techniques like singular value decomposition, SVD, which can be computationally very efficient, especially for high-dimensional data.
How does it use least squares for classification? Regression predicts numbers, classification predicts categories.
Good question. A key distinction is its typical label requirement for binary classification. While logistic regression usually uses 0 and 1, Ridge classifier generally requires the labels to be +1 and -1.
Ah, like we mentioned earlier, y plus 1 and minus 1.
By mapping the two classes to +1 and -1, the problem becomes directly analogous to linear regression. The model learns a linear function, weights times features plus intercept. When applied to a new input, this function outputs a continuous value. If that output value is positive, closer to +1, it's classified as the positive class. If the output value is negative, closer to -1, it's classified as the negative class. The decision boundary is implicitly where the output is 0.
So it's fitting a line or hypoplane and seeing which side of the line the point falls on.
Essentially, yes. It uses squared error loss, trying to make the output match +1 or -1 as closely as possible. This loss function is more sensitive to outliers than the log loss used in logistic regression, but the underlying optimization can be very fast.
Does Ridge classifier also use regularization? The name Ridge sounds familiar.
It does. The ridge part refers to ridge regression, which is linear regression with L2 regularization. So ridge classifier inherently applies L2 regularization by default, controlled via its alpha parameter, just like SGD classifier. This helps prevent overfitting by shrinking the weights.
Okay, so a least squares approach with L2 regularization, using +1, 1 labels. How did it perform compared to logistic regression for our zero detector?
When we look at its performance for the zero detector compared to the logistic regression methods, SGD classifier and logistic regression CV, ridge classifier generally showed a slightly lower recall for class 1, our zero digit. The recall was around 0.87, 0.88, whereas the LR models were often slightly higher.
So it missed a few more of the actual zeros?
Potentially, yes, in the specific runs shown in the sources. However, its precision was comparable to the other methods. So when it did predict Everone, it was about as likely to be correct.
Did its internal logic, those visualized weights, look any different?
Yes, and this is what's truly fascinating here. The visualized weight matrix learned by the ridge classifier appeared quite different, according to the sources, from those learned by the SGD or logistic regression classifiers.
Different.
It often displayed distinct black patches, where weights were strongly negative, and thus set to 0 or black for visualization purposes. This contrasted with other models that might have had small but non-zero weights in those areas. And perhaps surprisingly, it sometimes assigned significant weights to pixels right at the image boundaries, almost suggesting it was using the frame or the negative space around the digit more actively in its decision.
Wow, so it really sees the digit 0 in a unique way compared to the other models.
It seems so. It offers a powerful glimpse into the diverse strategies different algorithms employ to solve the same problem. Even when tackling what seems like an identical task, like the zero detector, their internal representations and learned patterns can vary significantly based on their underlying mathematical formulation and loss function.
Very cool. Okay, next, let's explore a seemingly naive but incredibly fast powerhouse, naive Bayes. The name itself suggests a simplicity, maybe even a flaw. But don't let that fool you about its power, especially in certain applications. What's its core principle?
Its core principle is built upon Bayes' theorem, a fundamental concept in probability theory. Bayes' theorem mathematically describes how to update the probability of a hypothesis based on new evidence. However, naive Bayes classifiers operate under a crucial, simplifying, and often literally naive assumption.
What's the naive assumption?
It assumes that all input features are conditionally independent of each other, given the class variable.
Conditionally independent, meaning?
Let's take text classification. If you're classifying an email as spam or not spam, naive Bayes would assume that the presence of the word Viagra is independent of the presence of the word free, given that the email is spam.
But that's probably not true, right? Those words likely appear together often in spam.
Exactly. In reality, those words are highly dependent within the context of spam emails. That's why the assumption is called naive. But this radical simplification, while often not strictly true in the real world, is what makes these classifiers computationally extremely fast and efficient to train and use for predictions.
How does that assumption make them fast?
Because they don't have to learn complex interactions between features. They just need to learn the probability of each feature appearing given each class. For example, p-free spam and p-free not spam, and the overall probability of each class. Calculating these probabilities is very straightforward, often just involving counting occurrences in the training data. They can process large data sets, even with thousands or millions of features, like words and a vocabulary, very, very quickly. And often the errors introduced by violating the naive independence assumption tend to cancel each other out, leading to surprisingly robust performance, especially in text classification.
Okay, so speed and efficiency are key benefits. And where do these naive Bayes classifiers truly shine? What are their primary applications?
This speed and efficiency make them a go-to choice for certain applications. As I mentioned, they are particularly well suited for text classification tasks.
Like spam filtering.
Yes, classic example. Filtering spam emails, identifying whether an incoming message is junk or legitimate based on the words it contains. Also, categorizing news articles into topics like sports, politics, technology, etc., or performing sentiment analysis, determining if a product review or tweet is positive, negative, or neutral. They excel where the features are counts, like word counts, or presence-absence indicators, and where the naive independence assumption doesn't severely harm performance. This is often true in high-dimensional, sparse data scenarios, like text, where most features, words, are absent in any given document.
Okay, this raises an important question. Given its naive assumption, which often isn't perfectly true, how do we choose the right naive Bayes classifier for our specific data? You mentioned different types earlier. The Sclaren.naive Bayes module offers a variety, doesn't it? Each tailored for different data distributions.
Yes, this is crucial. Picking the right variant makes all the difference because each one makes slightly different assumptions about the distribution of your features. Let's walk through the main ones offered by scikit-learn. First, we have Gaussian NB. This one is best suited when your features are continuous numerical values that you can reasonably assume follow a Gaussian distribution, the classic bell curve.
Like measurements, heights, temperatures, or maybe even our pixel intensities if we didn't scale them.
Exactly. Things like sensor readings, maybe some financial data. If your data values tend to cluster around an average with a certain spread, Gaussian NB is a strong candidate because it models the likelihood of features within each class using Gaussian probability density functions. Then there's multinomial NB. This is the workhorse for data that represents counts. Think word counts in documents.
So ideal for text classification where features are how many times each word appears.
Precisely. It's the go-to for many text classification scenarios, like categorizing movie reviews based on word frequencies. Here, features are typically non-negative integer counts. It assumes features are generated from a multinomial distribution. Next, complement NB. This is an interesting adaptation, specifically designed to work well with imbalanced datasets.
Imbalanced datasets, like our zero detector.
Potentially, yes, though it's often highlighted for text. Our sources mention that it frequently outperforms multinomial NB on text classification tasks, especially when you have class imbalance issues. If one category has significantly fewer examples than others, say, detecting instances of a rare topic in news articles, complement might provide more robust performance. It works by calculating probabilities based on the complement of each class, effectively focusing on what makes a document not belong to the other majority classes.
Interesting twist. What else?
Then we have Bernoulli NB. This one is used when your features are binary valued, essentially, yes, no, or presence-absence indicators.
So not counts, just whether a word is present or not.
Exactly. Think of it as indicating the presence 1 or absence 0 of a word in a document, rather than its frequency. For example, if you're classifying documents based on whether they contain certain keywords, Bernoulli NB would be appropriate. Each feature is assumed to be a binary Bernoulli variable. Finally, categorical NB. This classifier is relatively newer and is designed specifically for discrete features that are categorically distributed, but not necessarily ordered or numerical.
Like features such as color, red, blue, green, or region, north, south, east, west.
Perfect examples. If your features are distinct categories themselves, categorical NB is the one to use. It models the probability of each category occurring within each class without assuming any numerical relationship between the categories.
Wow, okay, so Gaussian for bell curve numerics, multinomial for counts, complement for imbalanced counts, Bernoulli for binary presence-absence, and categorical for discrete categories.
You've got it. Each variant applies the core naive Bayes principle, but adapts its statistical assumptions about the feature distributions, the feature class, to best fit the nature of your input data. Selecting the correct one is absolutely crucial for optimal performance, ensuring the model's assumptions align with your data's characteristics.
That makes the nuances much clearer. Let's see, naive Bayes in action now for that classic use case, text classification. This is where its speed and efficiency really shine. How did our sources demonstrate this?
Our sources demonstrated this using the well-known 20 Newsgroups dataset.
Right, the collection of online discussion posts.
Exactly. It comprises newsgroup documents neatly categorized into 20 different topics. For the purpose of this demonstration, the focus was narrowed down to a more manageable subset of just 4 categories. These included topics related to religion, specifically talk.religion.masic and soc.religion.christian, outer space, sci.space, and computer graphics, comp.graphics.
Okay, so a mix of distinct topics like space and graphics and closely related ones like the 2 religion groups.
Precisely. This provides a good mix for testing a classifier's ability to distinguish both clearly different and subtly overlapping topics.
Now, you mentioned text isn't immediately numerical. How do you convert those newsgroup posts into something naive Bayes can understand?
Right, that crucial pre-processing step. You need to convert that raw text into numerical feature vectors. The standard approach here is using the TFID vectorizer.
TF-IDF. Term frequency inverse document frequency. Break that down again.
Sure. It's a clever technique to quantify the importance of words. Term frequency, TF, measures how often a word appears in a single document. A word appearing many times might be important for that document. Inverse document frequency, IDF, measures how common or rare a word is across the entire collection of documents. Words that appear in many documents, like the globe EEs, are considered less informative and get a low IDF score. Words that appear in only a few documents are considered more discriminative and get a high IDF score.
So TF-IDF score is high for words frequent in one document but rare overall.
Exactly. It boosts the importance of words that are characteristic of a particular document or topic, while downweighting common words. This effectively identifies the signature words for each topic, like orbit and payload for space, or pixel and resolution for graphics, making them highly informative features for the classifier.
And how is this process implemented smoothly?
The entire process, from text conversion using TFID vectorizer to the classification using, in this case, multinomial MB, since TF-IDF often produces counts or weighted counts, is streamlined using a pipeline object in Sklearn.
Ah, pipelines again. Connect the steps together.
Right. The pipeline acts like an assembly line. You define the steps. First, apply the TFID vectorizer to the raw text, then feed its output directly into the multinomial MB classifier. This is a best practice because it ensures that when new, unseen text comes in for prediction, the exact same TF-IDF transformation learned from the training data is applied before it hits the classifier. It prevents data leakage, simplifies your code immensely, and ensures consistency and reproducibility.
Makes perfect sense. So what did the model's performance look like for this text classification task? Where did it do well, and where did the confusion matrix show it struggling?
The confusion matrix for this text classifier revealed some truly interesting and perhaps predictable insights. Categories like comp.graphics and sci.space were classified quite well. There was minimal confusion between them, meaning documents about computer graphics weren't being wrongly tagged as space documents, and vice versa. The distinguishing vocabulary learned by TF-IDF was likely quite clear.
But what about the 2 religion categories?
That's where, predictably, there was significant confusion. The sources highlighted that documents from talk.religion.mistusations were often misclassified as belonging to soc.religion.christian. A substantial number, 187 examples in the test set apparently, were mixed up in this way.
Which makes perfect sense, right? They likely share a lot of vocabulary.
Absolutely. Given their inherently similar subject matter and overlapping terminology, distinguishing between a general religious discussion and a specifically Christian one based purely on word frequencies is a genuinely hard task. It's a great example of how a model's confusion can often mirror real-world ambiguities or overlaps in categories. It highlights the difficulty even for an expert human to draw hard lines between such closely related topics based solely on the text.
Despite these understandable confusions, how did the model handle making practical predictions on new, unseen text snippets? Could it still make reasonable classifications?
Yes, despite those challenging overlaps, the model demonstrated its practical utility. It successfully predicted categories for new, unseen statements that were fed into the pipeline. For example, a statement like sending a payload to ISS was correctly classified by the pipeline as belonging to the sci-space category.
Okay, that seems right.
Another example, discussing Islam versus atheism, was accurately put into one of the religion categories, likely talk.religion.msde given the broader scope. And something like determining screen resolution was correctly classified as comp.graphics.
Great. So it demonstrates the practical utility and robustness of naive Bayes, coupled with TF-IDF and pipelines for quickly and effectively categorizing textual content.
Exactly. Even with its naive assumptions, it remains a workhorse for applications like text categorization, where speed, scalability, and decent baseline performance are paramount, even if perfect accuracy isn't always attainable due to inherent data overlaps or the limitations of the independence assumption.
Okay, we've covered a lot of ground. Logistic regression, SGD classifier, ridge classifier, naive Bayes. So what does this all mean when we bring together these different classification techniques? What are the overarching insights, the key takeaways we've gleaned from this deep dive?
Yeah, synthesizing this is important. We've seen several crucial themes emerge across all the models and examples, themes that really offer you, the listener, a shortcut to practical understanding. First, and perhaps the most important takeaway, there is no universal solution. We've clearly seen there isn't a single best classification model that just works perfectly for every single problem. Logistic regression, SGD classifier, ridge classifier, and the various naive Bayes classifiers each have their unique mathematical underpinnings, their distinct strengths, weaknesses, and optimal use cases.
So the choice really depends on the situation.
Absolutely. The choice often depends critically on your data's characteristics. Is it numerical, textual, categorical, high-dimensional, sparse, balanced, or imbalanced? And it depends on your specific problems requirements. You need interpretability. Is training speed crucial? How costly are false positives versus false negatives? You truly need to understand the tools in the toolkit to pick the right one for the job.
Makes sense. What's the second key theme?
Second, we've repeatedly seen the power and necessity of preprocessing. Scaling numerical features, whether it's pixel intensities for images using min-max scaler or transforming text into numerical vectors using t-fit vectorizer, is fundamentally important. It's not optional for many algorithms.
Especially those using gradient descent. Right.
Exactly. For many machine learning algorithms, particularly those relying on gradient descent optimization or distance calculations, scaling ensures that all features contribute proportionally to the learning process. It ensures that the optimization converges efficiently and effectively, rather than being dominated by features with arbitrarily large ranges. It's the often unseen, unglamorous foundation upon which good, reliable models are built. Garbage in, garbage out applies just as much to scaling as to data quality itself.
Okay, number 3.
Third, and critically, always look beyond simple accuracy. As our zero detector baseline examples starkly demonstrated, relying solely on accuracy can be highly misleading, especially when dealing with imbalanced datasets.
That 90% accuracy dummy classifier.
Right. A model that simply predicts the majority class can look fantastic on paper, but be utterly useless in practice, because it completely fails to identify the minority class you might actually care about. This is why metrics like precision, recall, and F1 score, along with diagnostic tools like confusion matrices and visual aids like PR curves, provide a much more comprehensive, nuanced, and honest evaluation of a model's true performance.
They show you where it's succeeding and where it's failing.
Precisely. They reveal whether it's generating too many false alarms, low precision, or missing too many true positives, low recall, allowing for targeted improvements or informed decisions about whether the model is suitable for deployment.
Got it. What's takeaway number 4?
Fourth, hyperparameter tuning is non-negotiable for optimal performance. We saw how critical it is to find the right hyperparameters, those settings like regularization strength or learning rate that you define before training. Methods like grid search CV for exhaustive search, randomized search CV for efficient exploration of vast parameter spaces, or specialized estimators like logistic regression CV, which automate tuning for specific parameters, are indispensable tools.
You can't just rely on the defaults.
You really shouldn't if
Yeah.
you want the best possible performance. Tuning is essential for optimizing a model's performance on unseen data, moving beyond arbitrary default settings to truly unlock a model's potential and ensure it generalizes well to new real-world examples. Neglecting this step is like buying a high-performance sports car and never bothering to tune the engine or check the tire pressure. You're leaving performance on the table.
Okay, theme number 5.
Fifth, we saw the elegance and practical necessity of pipelines. Using pipelines in Sklearn, or similar concepts in other libraries, streamlines the entire machine learning workflow, from pre-processing to prediction. By chaining pre-processing steps, like TF-IDF vectorization or feature scaling, directly with your chosen classifier into a single object, pipelines ensure that these transformations are consistently applied both during training and when making predictions on new data.
Which prevents mistakes, right?
Exactly. It prevents common and often subtle errors like data leakage, for example, fitting your scalar on the test set. It simplifies your code, makes your machine learning process much more robust, reproducible, and significantly easier to deploy and maintain in real-world systems. It treats your entire model workflow as a single, coherent, testable unit.
Excellent point. And the final key takeaway.
Finally, we gain some fascinating insights from interpreting what models see. Visualizing learned weights, like those 28 by 28 pixel patterns for MSTIS digits, or noting the distinct patterns learned by rich classifier compared to logistic regression, offers valuable clues about how these models interpret and prioritize different features in the data.
Peeking inside the black box.
Even if it's just a glimpse, it allows us to build intuition, even if slightly, into the mind of the algorithm. We can start to understand which parts of an image or which words in a document it deems most important for making a classification decision. This interpretability, even at this basic level, can be invaluable for debugging models, understanding their failure modes, building trust in their predictions, or simply gaining a deeper understanding of the underlying patterns in the data you're trying to model.
Fantastic summary. So, with these themes in mind, you, our listener, now have a shortcut to being genuinely well informed about the practical application of these fundamental machine learning classifiers. You understand not just what they are, but how they perform in real world scenarios, the importance of rigorous evaluation, and how to effectively choose and tune the right tool for your specific classification task. What an incredible deep dive into the nuts and bolts, the real practicalities of machine learning classification. We've seen the workhorses like logistic regression, the nuances of evaluation beyond accuracy, the diagnostic power of tools like the confusion matrix, and the sheer importance of finding the right algorithm and tuning it properly for the job.
It really has been fascinating to unpack. And seeing how different models, like ridge classifier versus logistic regression, can learn such different internal representations even for the same simple task.
Hmm.
This all makes me wonder, with all these different classification approaches and their unique ways of seeing the data, often making mistakes in similar predictable patterns based on inherent data similarities. What are the next frontiers? What's next for a model to truly understand the nuance and complex data, maybe going beyond just classifying it into predefined categories we give it?
That's interesting. Like, could models explain why they're confused between a 3 and a 5?
Exactly. Or perhaps even suggest new, more meaningful categories themselves, based on the subtle patterns or clusters they uncover in the data, patterns we might not have even thought of. Moving beyond supervised classification as we've discussed it today.
A truly thought-provoking question for you, the listener, to mull over. Where does classification go from here? Keep those curious minds engaged, keep exploring, and we'll see you on the next deep dive.